Okay, so in this lecture I will continue my overview of the history of the string theory landscape, how it came about, how it took its present form, and then very briefly in one slide I will mention a few of the more recent developments, more recent meaning basically after the day that the string landscape got its name, which is around 2003. So not all that recent. Okay, so this is where we ended last time. And so the point I was making so far is that, well, you know, there are a lot of Calabi-Yau manifolds and probably a lot of different topologies on which you can compactify. However, for our purposes, this is in fact not quite enough for, well, several reasons. So, well, one thing is, remember, we actually wanted like at least 10 to the 120 Vacua in some natural way. But in this case, if you just look at ordinary Calabi-Yau compactifications of, say, the heterotic string, even though this gives enough like the right amount of supersymmetry in 4 dimensions, it still has a lot of undesirable properties. And so at tree level, classically, the problems are that these compactifications always come with massless scalar moduli, which come, well, universally from the dilaton, but also from the shape and the size of the Calabi-Yau manifold. So these are just metric deformations that preserve supersymmetry, preserve Ricci flatness, and give rise effectively in 4 dimensions to massless scalars. And there can be a lot of them. And then, well, not, well, this is in particular an issue in, I guess, in type 2 constructions. You can have brain moduli and so on and so on. So now massless scalar fields are problematic. For one, we haven't seen them. Two, they give, you know, all kinds of light scales give all kinds of potential problems in cosmological settings and so on. They can destabilize the vacuum after supersymmetry breaking, etc. Okay. Of course, well, I was already implicit about what I just said. These compactifications have unbroken supersymmetry, so you need to break supersymmetry in some way, obviously. And also they have exactly 0 cosmological constant, which is related to the unbroken supersymmetry. Okay. So this is the case at tree level for these compactifications. Now you could say, well, okay, you know, that's fine, just classical, but there will be all kinds of quantum corrections. And in an n=1 theory, you know, they may, well, or you can generically expect them to get rid of the massless scalars, because there's nothing that protects the mass of scalars in the absence of supersymmetry. You know, these things may just take care of all these problems automatically. Now, this may well be, however, the universal problem you run into is a so-called Dine-Seiberg problem, okay, which was realized very quickly after the introduction of these compactifications again. Now, so these people have the questionable honor to have actually a problem named after them. And they didn't quite phrase it that way, but you can phrase it that way. So when corrections can be computed, they are not important, and when they're important, they cannot be computed. Okay, so this is a universal problem of physics. And, well, I'll give a little bit more details about that in the next slide. But so the upshot of this is that there's not even like a you know, marginally controlled way in these type of compactifications to establish the existence of the necessary 10 to the 120 positive cosmological constant Vacua, and so let alone actually do something useful with them. Okay. Now, a little bit more specifically, what's the problem here? So, okay. So first of all, they observed that you know, classically there is always so you always have the volume, the overall breeding mode, the overall volume modulus of the compactification manifold. So this is actually quite universally true. This is not only for Calabi-Yau compactification. It's basically due to the classical rescaling invariance of the Einstein equations. Now, right, so very good. So you have, classical solutions at arbitrarily large radii. At these large radii, you know that quantum corrections, which, whatever their origin is, or stringy corrections, will go to 0 because we know we can, trust classical GR at large scales. So if you look at some effective potential for dimensions induced by whatever quantum corrections, one thing you know for sure is that in the large volume limit of the Calabi-Yau, and this I indicate this modulus rho, in the large volume limit, the potential will definitely go to 0. Okay. Now there can be various quantum corrections, maybe instantons or whatever perturbative corrections, it doesn't matter, and they can go in two directions. So the first correction, so it will necessarily, again, fall off like 1 over the power of 1 over some power of 1 over rho, where rho is a volume modulus. And it could go, well, either like this, positively or negatively. Okay? Both are possible. Now, the first correction obviously isn't something you're really satisfied with, because in this case, you get a runaway, meaning the manifold spontaneously decompactifies. So it's not a compactification. And in this case, if you follow this through, well, the manifold just collapses, getting to substringy scales. So you definitely also lose control. Okay. So it is necessary to look at the next quantum correction, the next order, at least in a 1 over size expansion. So if you do that, well, for this case over here, you see then conceivably you could have a correction that reverts this collapse runaway and producing in this way a stable minimum. In this case over here, you need a little bit more. You need probably 2 corrections, like one that will push this thing down again, but then in order to avoid a runaway again to small volume over there, you need a 3rd correction that will push you up. But in any case, to get a stable vacuum at all, you need 2 corrections, and to get something with positive cosmological constant, you need 3 corrections. Now, if you have 2 or 3 quantum corrections that are necessary, that really make a qualitative difference, it means that quantum corrections are important, obviously. You're in a regime where the 2nd order and 3rd order corrections have a qualitative impact. Okay? Now, if that's the case, then, of course, you expect that the 4th, the 5th, the 6th, and so on order corrections will also have an important impact. Okay? And so therefore, it's very, very hard or impossible generically to control these situations, simply because you need quantum corrections to be important to get a stable vacuum at all. But once they're important, it's very hard to compute anything at all. Okay, so that's the Seiberg's problem. It's a very, very simple argument, and as usual with very simple arguments in physics, it's very difficult to get around it, and it's basically still plaguing all attempts at constructing controlled string vacua to date. Okay.
Can you imagine some situation like Banks Sachs where you can say that the first question is important, but then
that what is important?
So in a Banks Sachs exponent case, like you see that the first quantum question is important for the second one, but then for the other one it's negligible. So you can cook up the example where.
Well, over here the problem is, you see, if only the first quantum correction is, if you only have the first quantum correction, it will go like 1 over rho to some power, and so then you're in this situation, okay? So
I was just wondering whether there's something like this strange situation where that kind of stuff happens.
Well, in a certain, it may, with the addition of the element that I'm going to introduce now. So actually, I guess the answer is yes, and it's what KKLT figured out. So I will get to that sort of, but it's not okay. Morally, the answer is yes, I guess, but you need more ingredients. Okay. So the situation since '85 improved a little. In large part thanks to the advent of so-called flux compactifications. And so these were, discovered over many years in various forms. by various people. So the oldest ones go back to the 80s. Then there was Strominger in '86 in the paper that I showed you the conclusions of. So this was in the heterodox string. Then in type 2, Polchinski and Strominger in '95. Then in M theory, the Becker sisters, and then this. So basically these study the flux compactifications, which have then turned out to be most useful in various constructions. Okay, so what's the basic idea? You can, on the internal manifold, so string theory in general has various Ramon, Denef-Schwarz p-form fields, p-form fluxes, and just as magnetic, Maxwell magnetic fluxes, you can just turn them on. You can turn on quantized fluxes measured by integrating this form to various non-trivial cycles in the manifold. Okay, and so with some suitable normalization, it means that the periods, sort of the integrals of the fluxes over these cycles, are given by integers. Okay, so we integrate a p-form flux over a p cycle. Of course, the fluxes have just quadratic, appear quadratically in the action typically. And the effect is that in 4 dimensions, effectively, this will look like generation of an effective potential, an effective energy density. Okay, and you can just read these off from the effective action, from the action for these fluxes. So that's this thing. This factor over here you get from going into the Einstein frame in 4 dimensions. Right? So if you do the standard reduction to 4 dimensions, initially you get the volume of the Calabi, or the volume of the compactification manifold, the volume of the Calabi-Yau in front of the 4-dimensional Einstein-Hilbert action. So it's some sort of a dilaton type field. In order to get standard Einstein gravity, you need to rescale the 4-dimensional metric by some power of the volume. And if you do that, then effectively in the potential, you get an additional factor of 1 over the volume of the Calabi-Yau squared. Okay. All right. So very good. So now you get an additional contribution to the potential. You no longer have this exactly flat situation that we had earlier. So maybe this is good enough, who knows, to stabilize us. Now, if you look how this thing scales with the overall scale of the manifold, with this modulus that I called rho before, right? Then you easily see that this is not the case, that you get actually a runaway to large volume. Okay, so it's more formally, what I'm doing here is I just rescale the metric. So I write it as r squared times some standard metric with unit normalized volume, and then I just do the trivial scaling, and I see I get a 1 over r to the k. K is the dimension of the compactification manifold plus 2p, where p is the degree of the form, right? These are p forms. Okay, so all of these give you a potential that looks like this. Okay, so that's not good. However, we have not included everything, because there's also the Einstein-Hilbert action in the compact manifolds, and this could conceivably give rise to a contribution with a different sign, and therefore maybe could stabilize the internal manifold. Okay. So if you add this term, then again, simple scaling reasoning as before tells you that this goes like 1 over r to the 2 plus k. And so then you see there's different cases to consider. Okay, the first case, well, when the internal curvature is just exactly flat or Ricci flat, then this drops out, and we are in the previous case, so we have a runaway. When the internal curvature is negative, right, then, well, this term is positive, so you get an even worse runaway, so that's no good. Now, if the internal curvature is positive, like a sphere or something, then in the case that p is greater than 2, you see that the curvature term at large radii dominates. Okay, so that means that the potential at at large radii will be of this sort, right? It will go down. But then at small radii, or at smaller radii, you see that this one, the positive one, starts dominating, and the thing will go up. Okay, and so in this case, you see you get a minimum necessarily at negative cosmological constant, right? Because the thing first goes down and then goes up. And so in this case, you get indeed an ADS vacuum. And of course, you know many examples of this. For example, ADS 4 times S7, compactification of M theory is an example of this. More generally, all Freud-Rubin compactifications. Okay, so it's easy indeed to construct such examples. Okay. Now the problem usually with these compactifications is, well, apart from the fact that they have negative cosmological constant, which is not necessarily what we want, is that typically, like in the Freud-Rubin compactifications, you get that the ADS radius is of the same order as the compactification radius. So you don't really have a compactification. You don't really have a hierarchy between KK scales and ADS scales. And you might say, oh, well, okay, but now then I break supersymmetry and then I lift the whole thing to positive cosmological constant. The problem with that is, because these two scales, the cosmological constant scale in the four-dimensional theory and the KK scale are of the same order, it means that whatever you add to lift the whole thing has to be an energy, of the order of the KK scale, and so automatically, again, you lose control. Okay. So, okay, these give vacua, but it's not quite what we want. Fourth case, if P equals 1, if P is exactly 1, so these are one-form fluxes, which means basically just scalar gradients, like axiom gradients. Then you see you can get exact cancellation because these scale in exactly the same way. So if you tune the curvature to compensate this term, you just get a flat potential. And indeed, such vacua exists. These are, basically type 2b compactifications with varying axiom dilatons. So these are also known as F-theory compactifications. And then finally, the case P equals 0, so zero-form fluxes, which is basically like adding, a cosmological constant to the theory, a quantized cosmological constant. So these theories are known as, or this theory basically is known as massive type 2a theory. In that case, things get a little bit more subtle because you see now this one becomes a dominant term at large radius. So and if you add more fluxes, you might imagine, that the various contributions can actually classically stabilize the compactification, and you might hope maybe even at a de Sitter minimum. But at least the best controlled examples of this, or in smooth cases, show that actually the vacua you get are again ADS type vacua, again with cosmological constant and KK scales of the same order. All right. So one thing that we note here out of this very simple analysis is that there's just no way apparently to get a classically smooth de Sitter compactification. And indeed, even if you extend the ansatz, so we made a very simple-minded analysis, just a direct product, no warping and so on. But even if you allow for warping, even if you allow this warp factor in front of the four-dimensional metric, you can show that it will still not work. Okay, so this was first discovered by Gibbons in '84, and then rediscovered by de Wit and collaborators in '87, and by Maldacena Núñez in 2000. And so basically what this theorem says is that there are no smooth classical de Sitter compactifications of Einstein gravity coupled to massless fields, or massless P-form fields and stuff, with possibly a non-positive cosmological constant added. So you don't get de Sitter ever, and you also don't get Minkowski if any of the fluxes is non-zero, except in this case when you have one-form flux, which is the F-theory case. Okay, so there you go. So this has been refined in various ways, most recently by Douglas and Kalash, where they closed a number of loopholes that were still in this theorem. Okay, so this is basically the core of the problem. Like, if this wasn't the case, we could have happily constructed, classical de Sitter compactifications and well, I don't know what the world would have looked like, but it would have looked very differently. But this is not the case. It's actually very remarkable. So for some reason, string theory or higher dimensional gravity theories abhor the Sitter space. They really don't like it. Okay. Now, this is really too bad. This is too bad because Busso and Polchinski, in around the same time as Mandersen and Nunez wrote their paper, pointed out that actually, if this problem wasn't there, if you just could have the Sitter flux compactifications, then fluxes can give you exactly, very naturally, these 10 to the 120 or even more vacua that you need to solve the naturalness problem of the cosmological constant. Okay, and the model they presented to make this clear is very simple. So it's the following. So first of all, as I said, let's ignore this Nogo theorem, right? Or suppose that we manage to exploit the loophole. So we'll actually talk about the loopholes in the next slide. So let's say that we do have these stable vacua. Let's in particular, consistent with this, ignore the moduli. Okay, let's say that God has frozen the moduli for us, and we don't have to worry about it at a particular value. Okay, so the only degrees of freedom are flux quanta, and I, where I ranges from 1 to b, and b is sort of is a number of flux quanta of a certain type, which is set by the number of independent cycles of that dimension in the Calabi-Yau, which typically can be like hundreds, thousands, even sometimes even 10,000s, millions. I mean, but hundreds is like typical. It's hard to get actually under that. Okay, so then the cosmological constant. So the contribution from the fluxes, just from this f squared term that I showed earlier, will be quadratic in the flux quanta, right? With some metric which is determined by the internal metric and whatever, but this is a frozen constant, and then some overall energy scale, which I'll call mu to the fourth. Okay, so there's this contribution, and then let's say that there's some contribution from curvatures and so on that is negative, and it looks like a minus m to the fourth. Okay. All right. So the situation then is, in order to get a cosmological constant which is very small, very close to zero, basically what we need to do is find lattice points in a very high dimensional lattice which lie on a sphere of radius approximately m to the fourth, or radius squared approximately m to the fourth. So this lambda naught here is actually this minus m to the fourth. Okay. And so in order to find, in order to have any vacua with such a small cosmological constant, what you need is to have some lattice points lie inside of this shell with sort of thickness 10 to the minus 120 compared to the fundamental scale. And in that case, you do have the kind of vacuum you want. Now, this may, to lower dimensional intuition, this may look ridiculous, but what they pointed out is that in a high dimensional space, it's in fact very generic that you have such a thing. Okay, and so the way to estimate the number of lattice points that you expect inside of a spherical shell, thin spherical shell, what you do is just compute the volume of this shell, right? And the volume of this shell, properly normalized, should give you an estimate for the number of lattice points that you expect inside of that. Okay, and the volume of the shell is of course easily computed, just for the volume of a n-dimensional sphere, b-dimensional sphere. Then you apply Stirling's formula, and the end result is this: 2 pi e m to the fourth divided by b mu to the fourth. B is the number of fluxes to the power b over 2 d lambda. Okay, and d lambda is the thickness of the shell. Yeah? Is this clear? Okay. And now, essentially, because of this power here, it is easy to get huge numbers from, modest ingredients. So, for example, let's take this scale over here, so the curvature-induced negative cosmological constant, to be say 10 to the minus 2 times the Planck scale. Let's take this energy scale mu in front of the flux contribution to be 10 to the minus 3 times m Planck. Let's take the number of fluxes 100. Then when you plug in the numbers, you see you get the n of the order of 10 to the 160 d lambda. Okay. So in particular, taking d lambda to be 10 to the minus 120, well, there's some m Planck here probably. I've been a bit sloppy with the dimensionful. I guess there's an overall divide by m Planck to the fourth here, something like that. Okay, so you see then you still get 10 to the 40 vacua within that very thin shell of thickness 10 to the minus 120. Okay, so this is just because it's a high-dimensional space. In a high-dimensional space, you get everything is either like exponentially large or exponentially small. So.
Do these GIJs somehow have the quantum corrections in them?
Quantum corrections?
Yeah, right. I mean, so you were previously saying that if we actually wanted to compute the cosmological constant for any of these vacua, we'd have to compute some quantum corrections.
Yeah. So, well, so you mean what I said previous, or you mean like compute in the sense of like actually get the exact number?
Yeah.
Yeah, so okay, so this is a total toy model, obviously, right? So in any realistic setting, well, definitely, I mean, the main thing is you have to take into account the fact that these things are coupled to moduli, and they will typically, very heavily influence like the whole stabilization of the thing. But then, okay, say that even that you can get that under control, you also have to, I just argued that actually these don't exist classically. So,
right, yeah, but there's some assumption that maybe I should postpone this question until you talked about KKLT, but there's some assumption that this distribution doesn't change too much.
Oh, yeah, that's right. Okay, this is something we can definitely talk about later, but this is an important point. So indeed, for an individual vacuum, it's sort of hopeless, obviously, right? If you really want to check of an individual vacuum that the cosmological constant is 10 to the minus 120, you have to, go up to like, 30 orders in perturbation theory in the standard model, which, it's not even possible. So you can do it, but distributions are much more robust in general, right? Because so the typical scales of variation of a distribution is sort of, more like the fundamental scale, okay? So that will be sort of the scale at which you see features. And now if you start, introducing corrections, this distribution can sort of move around, right? But it will not, unless you have a distribution that looks like, like some very sharp peak, and you're interested here, and then like, there's a correction that moves this from here to here or something weird like that, you won't have like gigantically drastic effects. Unless, of course, for some reason, the vacua don't exist at all.
Yeah, what if it pushes them all away from the center somehow,
it's certainly something to worry about, but generically, distributions are much more robust than, right. It's sort of the law of large numbers as well, right? Like, you do, it's the... Yeah.
Works except when it doesn't.
It works pretty well, anyhow, but we'll definitely come back to that later when we do more serious type of statistics. Because at this point, obviously, this is such a toy model that it Sorry? How
does each lattice point correspond to
correspond to vacuum state?
Yeah.
Okay, so it kind of comes from, so the basic idea is, you just look at string theory compactified on this manifold. String theory has these p-form fields, right? P-form field strengths. So you can turn those on, you can turn them on, you can give them sort of non-trivial fluxes through various cycles, right? Which are parameterized by integers. Yeah, so sort of internal magnetic fluxes, right? Then, in principle, you would still have to solve, of course, the Einstein equation, the full equations of motion. So there's back reaction of the fluxes on the internal manifold, and as I just argued, that actually causes the whole thing typically, if you want positive cosmological constant, to decompactify and so on. But let's now say, for the sake of the argument, let's ignore that. Let's ignore back reaction. Let's just freeze the moduli. Let's just freeze the background, right? So this metric that appears here, just freeze it to keep it constant. And now we turn on these fields, these fluxes, okay? So when you expand, so you can expand these, well, so essentially you see from this equation that these f's are proportional to these integers, right? And so if you plug these into, so if you use that in this expression, you see you get over here an expression which is quadratic in those integers, okay? And if those are the only degrees of freedom, what you get is an expression of this form, okay? So this is just the most general quadratic expression of, so these are integers, right? So you just choose these integers. This is just the most general quadratic form, right? I'm summing over I and j here.
Which lattice point correspond to the integer number?
Oh, yeah. So that's right. So each set of integers from 1 to b corresponds to a lattice point in a b-dimensional lattice. Okay, I think that's, yeah. So, yeah. Okay. But so the main lesson from this is that high-dimensional spaces are quite counterintuitive. And just as an aside, to mention a few remarkable things, is that in the limit where you take the dimension of a space to infinity, if you look at a ball of some radius r, then you will find, you pick just two random points, you will find that with probability 1, these 2 points lie exactly at the boundary of the sphere. Moreover, any 2 points you pick, right, will always be at a distance square root 2 times r. Okay, now this may seem really weird, but it's actually less weird if you think about it in the following way. So take 2 random points. Okay, so these are 2 random points which you can think of as lying on a sphere of radius r. Okay, so they're normalized, a very large vector with normalized length. Now you look at the dot product of these 2 random vectors. Well, since they're random vectors, they're uncorrelated, so this dot product of the 2 will be 0, right, in the large dimension limit, because they're uncorrelated. So if the dot product of 2 vectors is 0, it means that they're orthogonal to each other, and if they're orthogonal to each other and they have each length r, it means that the distance between them, between the endpoints, is square root 2 times r. Okay, so all distances in a high-dimensional space are all the same. I mean, at least in this simple spherical case. All right, and then the third one is, as you can actually already see over here, that the volume at fixed r vanishes, okay, in the large dimension limit. So if you look at this formula, you see when you send b to infinity, keeping everything else fixed, this whole thing goes to 0 again, okay? So that basically means that the volume estimate becomes a bad estimate, because obviously there will still be lattice points. But it's just something to keep in mind, okay? All right, so basically what this means is if you look at the cube of rate of side r, and you look at the sphere inside of that, and in the infinite dimensional limit, basically all points of the inside of that cube will actually be outside of the sphere. All right. Moreover, you get all kinds of intractability problems in high-dimensional spaces. We'll probably come back to that. But so, for example, this problem I mentioned of like, well, you have to just find lattice points inside of a sphere if you have to figure out whether or not there are lattice points inside of the sphere. So in general, well, when you can do an estimate and the numbers are large, you know for sure that there will be lattice points inside there, and it may even be not too hard to find an example. But in general, so I say in the marginal cases where maybe there's a few lattice points expected, it's a computationally very hard problem to figure out even if there are any points or not. And you can actually prove that provided P is not NP, that there's just no general polynomial time algorithm to figure out this question. So you run into all these kinds of interesting problems.
But that's only true for infinite dimension, or it's true for any large?
It is no. So these issues of computational complexity, they are statements about finite size problems, but how the computation time scales with the size of the problem. Okay, so typically the size of the problem meaning basically the number of digits or something you specify the data with. And so polynomial time means that the number of steps to solve the problem is polynomial in the number of digits of the input data and exponentially. So it's but in practice it means that if you have a few hundred lattice points and you're in a situation where the expected number of points inside of the shell is just of the order of a few, the problem is effectively intractable. Okay, unless you have to just try out everything, which will take exponentially long. Okay, so right. So this gives actually, it gives a sort of paradoxical situation that say that if we found some sort of you can generalize this to other situations, but say we found some sort of a very strong selection mechanism that tells us, like cosmology selects the vacuum with the smallest positive cosmological constant. Right? That wouldn't mean we actually could find it. You see, like even if we knew this was true, it might still be totally impossible to actually find it because like something that gives you a very sharp selection mechanism means that you have a few solutions only, and typically then solving the problem is intractable. So it's kind of a perverted situation. All right, but anyway, obviously, having fluxes can be, well, looks like exactly what we want in order to solve the solve the naturalness problem associated to cosmological constant.
About the repeatability, is the statement like if I'm given the data, then it would take me exponentially long amount of time to sort through it and find the one that.
Yes, but of course there can always be instances that are easy. Okay, so or if I give you the solution, of course you can check that it's the solution. Right. But so the statement is that in general, the more precise statement is that if you can devise an algorithm that solves this problem guaranteed in polynomial time for any kind of input that you can cook up for this problem, right, then it means that everything we ever thought is hard is actually easy. Okay, so then you have shown that NP equals P, and you win the Clay Prize, and so.
What's the input data then?
Okay, the input data in this case, yeah. So, right. So the input data is this number M, is mu, is a GIJs, and then basically epsilon, which is the width of the shell. Okay. So the way this is, you can prove that this is the case is by showing that if you have a polynomial time algorithm to solve this problem in general, right? For general input M, mu, Gij, then you automatically also have a polynomial time algorithm to solve the so-called subset sum problem. Now, what is a subset sum problem? That is, I give you a list of n integers, and I ask, is there a subset that sums up to 0? Okay. Now, this is a well-known and so-called NP-complete problem, which is a problem in the class that is a problem that is such that if we have a polynomial time algorithm to solve that one, then we have a polynomial time algorithm to solve any problem in the class NP. Now, what is the class NP? The class NP is not non-polynomial, but it means the class of problems of which the solution can be verified in polynomial time. Okay, but it includes like all the classic hard problems, like the traveling salesman problem, the knapsack problem, all of these.
The statement is that if NP is not equal to P,
yeah.
To find these integers,
in general,
it takes exponentially long time.
That's right. Yeah, except in easy. I mean, obviously, if I take the shell like of width like 100,000, then the problem becomes easy. I just pick any point and I will be in there. So but the question is, can you do it for can you have an algorithm that guarantees you a solution for any input?
Somehow it's exponential, like 1 over epsilon.
It's a little, yeah. So it's a little tricky. So because there's several regimes. Also, when epsilon becomes extremely, extremely small, then again, when epsilon is 0, for example, clearly there are no solutions. So there's some sort of a crossover domain where the complexity peaks, which is where the number of solutions is sort of order 1. And that's the hardest. Yeah.
Why is it that, general vectors would be orthogonal to each other?
Am I wrong in that? So we basically have two vectors, vi, I going from 1 to n, okay, and wi.
This is a probability statement that you are saying I cannot find a vector which is not orthogonal to a given vector.
No. So there will of course be vectors which are not orthogonal, but with probability, like in the large n limit with probability 1, it's just because you have basically a it's so you normalize this one, say, to 1, okay, and then it just becomes, well, if you take a dot product, you basically just have a random walk, so you get square root of n, but then you divide it by, n, so that goes to 0 in the thermodynamic limit. But yeah, of course, and if for some reason the probability distribution is different than just the uniform one, then also you can get more structure, and in fact, in many cases, like in spin glasses and so on, you actually get much more structure than just this. All right. Anyhow, so because of what Busso and Polchinski pointed out, it was clear that probably this whole set of ideas were worth a little bit more effort. And indeed, in 2003. Kachru, Kalosh, Linde, and Trivedi figured out a way to basically evade these Nogo theorems and come up basically with an exponentially large landscape of flux vacuum, including cases with exponentially small cosmological constant. Okay, so this Maldacena, Nunez, Gibbons, etc. Nogo theorem has a number of loopholes. So one is it only applies to Einstein gravity. If you have higher order curvature corrections, then it doesn't hold, like R squared or whatever. Also, if you have orientifold planes, which are singularities, with negative tension, the theorem doesn't hold. And more generally, of course, once you allow quantum effects, the theorem doesn't apply because it's a classical theorem. Okay. Now, all of these loopholes involve the fundamental length scale, so it will always be small when all scales are large, right, as expected. So necessarily, we're going to run into some sort of a version of the Dine-Seiberg problem again. Okay. However, these people gave reasonably convincing plausibility arguments that with the following ingredients, this could basically be done. So first of all, they looked at type 2B theory on a Calabi-Yau 3-fold orientifold, like an O307 orientifold, which is equivalent, if you want, to F theory on a Calabi-Yau 4-fold. They switched on Ramon and Neveu-Schwarz 3-form fluxes, which stabilizes a large number of the moduli already, but not the size modulus. Then they considered quantum corrections in the form of D3 instantons and gauge genocondensation on 7 branes that you have in this theory. These give contributions to the superpotential, exponential type corrections to the superpotential, which do depend on the size moduli, and therefore give a potential for those. And then finally, so with these ingredients, you already get vacua with negative cosmological constant, including with very small negative cosmological constant. And then to lift this then to vacua with positive cosmological constant, they considered some anti-D3 brane put at the bottom of some strongly warped throat in this compactification. Okay, so it looks a little bit baroque, but this is what you need to do to get around these Nogo theorems. Okay. So with these ingredients, they noticed that all moduli are stabilized, and you actually do have some control. Now, where does this control come from? Why don't you have the Dine-Seiberg problem again? Well, in general, you do have the Dine-Seiberg problem again. So the generic vacuum here will again be not controlled, but precisely because you have so many flux vacua here, there's so many choices of flux, you can argue that out of, like, let's say, 10 to the 500 that you get, to just name a random number, there will be a very tiny subset of those, but tiny just as relatively tiny, can still be like 10 to the 100 vacuum in there, for which the classical contribution to the superpotential, to the potential, just happens to be accidentally exponentially small, therefore allowing balancing with a non-perturbative effect, which also is exponentially small, right? So in general, okay, I should do something like that, okay. Right, so the superpotential that you get in these theories schematically will be of this form. This is a contribution coming from the fluxes. So this is a classical contribution. This is a contribution coming from the quantum effects from the instantons. Then to find like a supersymmetric vacuum, which is what you do before this last step over here, you have to solve this equation, right? Where this is the scalar covariant derivative, right? This, okay, which you can do basically, where the solutions of this equation will be such that this term here balances against that term. So these two have to be of the same order. Now, in general, for the generic vacuum, this contribution will be of order 1, and therefore this T will be sort of order 0, and the whole thing will be completely uncontrolled, the usual Dine-Seiberg problem. However, since there can be exponentially many of these flux vacua, this W naught can easily become exponentially small, and in that case, these two can balance with a reasonably large value of T, right? T can be, well, T in this case is the size of some force cycle inside of the manifold. So this can be reasonably large, and the whole thing can be reasonably controlled. Okay. All right. Now, each individual vacuum, again, control will be sort of marginal at best, but nevertheless, it's very hard to believe that with all these ingredients and this rather plausible existence of minima, that you wouldn't get any of these at all. And once you accept that you have some of these vacua, then, well, you automatically get exponentially many. Okay. So, mission accomplished. This, the holy grail of this kind of string theory was reached. The sitter, vacua with positive cosmological constant, as small as the one we observed. And shortly after, the landscape got its name by this paper, and once it got its name, then, it existed, I guess. Interestingly, so this was actually in 2003. This is from his previous paper, and forgot to change it. Unless it was some fraudulent attempt to. I don't think so. Okay. So that brings us to the present then, right? Once the landscape got its name, let's say that everything after that is the present. So a lot of work has been done after that paper. Of course, I cannot review all of that. It's 1,000 and something citations. But let me mention some of it. So first of all, of course, obviously, since they pointed out that with high plausibility you have this long-lived metastable vacua with positive cosmological constant, this looked also very inviting to try to find realizations of slow roll inflation. Okay, and so these people looked at this and found that it's actually still pretty hard, and you still need to fine tune and so on. But okay, there are reasonably swallowable scenarios of slow roll inflation, even though it's still hard. Okay, now then, there's this. The issue that was raised before, sort of like the whole, Busso-Polchinski idea of like not, of trying to estimate numbers rather than, to get like individual vacua, can be generalized and can be made much more systematic, and can be extended to various quantities, and in particular can be extended to to the actual full problem where you let moduli and so on back react. This was done by these people, and so various interesting results were obtained, some of which I will mention later. But one thing this made precise, for example, is this possibility of taking this exponentially small. Other results were results on the distribution of the supersymmetry breaking scale, etc. Now, Kachur, Kalos, Lin, and Trivedi actually did not give explicit examples of their construction. So in particular, for their mechanism to work, they needed certain instant contributions to the superpotential, which puts like very restrictive conditions on the topology of the compactification manifolds, which is sort of hard to verify. But explicit examples were found, which were sort of, marginally controlled, but nevertheless, as a proof of principle, they were discovered soon after. Then there's all kinds of interesting particle physics consequences of this sort of new notion of naturalness that the landscape induces, right? So there's sort of this, as I said before, naturalness has always been a very important guide in getting to new theories and in sort of guiding us to propose new theories. And there's the old notion of naturalness, technical naturalness, saying that something is only zero, when you have a particular symmetry that forces it to be zero. And so this has led to many discoveries of symmetries as underlying structures of physical laws. But here we arrive at a new kind of naturalness where, for example, the cosmological constant is extremely small, not for any reason, but just basically because of statistics. It can be small, and then there's a post-selection mechanism on the existence of structure, which then forces it to be small. Okay, so this changes the notion of naturalness somewhat. Similarly, you can make arguments a little bit weaker, but still pretty reasonable arguments on the supersymmetry breaking scale, on the electroweak scale. And so it makes perfect sense then to contemplate what the consequences are for what we expect, basically based on this new notion of naturalness, right? Just granting that this landscape picture is correct, what do we expect? And so this has led to various very specific scenarios, which people are looking for now at LHC, the split supersymmetry, et cetera, et cetera. Okay. A certain number of variants, in particular this one of KKLT, was proposed, where, so in the one here of Balasubramanian, Berkelund, Conlon, and Quevedo, instead of balancing these non-perturbative effects against some exponentially small classical contribution to the superpotential, they balanced non-perturbative effects against perturbative effects. And in general, you might think this leads to just a reinstatement of the Dine-Seiberg problem. To some extent, this is true, but again, they argue reasonably convincingly that this nevertheless leads to well-controlled compactification, and in fact, better controlled than the KKLT ones. And it's some.
So what are these perturbative effects? Like these are.
So there's the first perturbative correction to to the Kähler potential, right? So the superpotential doesn't get any perturbative corrections, but the Kähler potential, which to leading order, so the Kähler potential of the four-dimensional n=1 theory, which to leading order is something like minus, and then I think it's 3 logarithm of the volume, okay, gets a correction over here, which looks like, I don't know, it's some alpha prime stuff, G string, whatever. Okay. Right. So this will break this no scale structure of the potential a little bit, and so basically this gives some a volume. So this gives this gives a volume suppressed correction to the potential. Then you have here an exponentially suppressed contribution to the potential, and you let these two balance against each other. Now, this over here is the volume of some particular force cycle wrapped by the D3 instanton, and this is the overall volume. Okay, so they said, well, okay, so this force cycle they take to be, sort of smallish, not super small, but smallish. So this is a very small number, and then the volume they take like very large, so that you can get this balancing. So you get some sort of a skewed manifold with And this can be made to work in a particular class, in particular of Calabi-Yau manifolds, which are called Swiss cheese manifolds, basically because, the expression of the volume for them has a form of, something large minus a number of small holes, like Swiss cheese. Okay. And so they wrote a long series of papers on this. This here? Well, so this depends. You mean in this? In the scale of T is set by right. So it's essentially controlled. Okay, so you get a particular equation for this, but this equation still has. It also depends on complex structure moduli, and in particular on the dilaton. Okay. Now the dilaton is stabilized by fluxes. Okay, and so you can basically, again, so that because there's exponentially many flux vacua, you can sort of tune the dilaton pretty much any way you want, and this volume over here is going to actually has exponential dependence on the dilaton. The reason being that, well, it appears over here as a 1/G string here, and then so you can get. In principle, you can get vacua with just gigantically large compactification manifolds, even though the masses involved will be exponentially small. To offer it. All right, what else was done? Well, more corners were explored, in particular by these people and others. Oh, sorry, I skipped the 2A one. Yeah, so in 2A, you can actually stabilize all the moduli and get a scale hierarchy between a KK and the cosmological constant, just purely classically. However, you get ADS vacua, and in fact, you can even prove that it's even impossible to get slow roll inflation in these vacua unless you add a whole host of new complicated ingredients, and this is, well, in particular, Eva Silverstein has looked at several of those constructions. Right, but so they don't get any easier, to say the least. Okay. Then, as I already mentioned, the computational complexity of these vacua was of the landscape basically was studied. Like, whoa. Then the very dicey issue of, is there a proper notion, is there a good notion of probability measure on these vacua was explored by various people. And then, well, very few people have tried to say something about the entire landscape of string theory, not just like these particular models, but just start with the most to begin with, a full solution set of supergravity. But even that is not enough because, you might imagine solutions of the full string field theory or whatever. But so in particular, Mike Douglas has done some has made some recent progress in understanding this. All right. So, very good. So this brings me at the end of the general broad overview, and I will now get into more technical details. And for that, I will actually switch to the blackboard. Okay. And let's Okay. So let's have a look in more detail at some landscapes. And it starts with landscapes without gravity, which for various reasons are easier to study, conceptually simpler, but nevertheless, all of the technical ingredients that have been useful in the gravitational landscapes can already be fully appreciated here. Okay. And I will talk about two cases. One is spin glasses. Second one is D-branes, but D-branes not filling all of the visible space, but localized at a particular point so that you can actually take the limit of arbitrarily large charges. Okay. All right. Now, so the reason I'm talking about spin glasses, even though they have nothing to do with the string theory landscape, or at least not that we know at this point, is that this is an example, where landscapes have appeared in physics and where physicists, over the course of many years, and basically from 1975 or something to 1985, have developed a very elaborate and very beautiful theory where, basically the complexity itself, the structure itself of this landscape was central, leading to various interesting, physical behaviors and so on, and also leading to various very interesting mathematical structures. Okay. Now, many of the techniques that were developed here, like sort of replica symmetry breaking and the structure of ultrametricity and so on, have not found any applications yet or haven't been applied yet to string theory. And I think in part that's because most string theorists don't know these techniques. That includes myself. But so nevertheless, let me try to say a little bit about it to basically give you a taste of what is possible and what people have done, right? Beyond just saying, "Oh man, this looks complicated. Let's go do something else." Okay. Right, and then so I will introduce D-branes. So you can actually talk about flux vacua and so on in the context of D-branes as well. These are world volume flux vacua. Then they have like interesting landscape-like structures, and but okay. So there's a few there's a number of advantages compared to the gravitational ones. One is that you can take the charge as arbitrary and not like bounded by tadpole cancellation conditions, which means, in particular, you can take some large n limits really. And then secondly, these D-branes have sort of gravitational duals, right? These are field theories, but they have gravitational duals, in particular black holes. Okay, and so you can test for example, counting formulae for number of vacuum and so on, by comparing to just four-dimensional black hole entropy formulae. Okay, so that's interesting by itself. Okay, moreover, the actual D branes that we're going to look at, which are D4, D2, D0 branes in type 2a, localized at a point, actually have direct mathematical counterparts, or physical counterparts, in type 2b theory as D7, D5, D3 branes, right? If you just look at the D4, D2, D0 brane wrapped around some cycle in a clavier, localized at a point in space, now you look at exactly the same object, but space filling, you get a D7 brane in type 2b theory, and this is exactly the corner of the landscape, which for various reasons is most interesting. So it's where KKLT works, it's where you can get slow roll inflation, it's where this F-theory constructions, F-theory guts and so on are happening, there's where particle physics work very well. So this is really the in a certain sense, the most interesting corner of the landscape, sociologically speaking. So the D-branes that we will consider are basically direct counterparts of those, or the structure is very much the same. So that's another motivation to look at that. Okay. So let me start with spin glass. Now, what is a spin glass? A spin glass, for example, you can get by taking copper and then just sprinkling manganese atoms sort of randomly throughout the copper lattice. So this copper, this manganese. Okay. So these atoms have particular spins. Okay, you can just naively imagine some sort of classical dipoles or something like that. And these spins interact with each other, but the interaction potential so the spin-spin interaction potential oscillates, okay, with distance. Okay. Sorry? The spin of manganese, 1 and the double. It doesn't matter. I mean, it's just an example. Yeah. I don't know. What? I think these are classical spins. Yeah. Sorry?
What do you mean the spin is 1?
I don't know. I'm thinking of these are like atoms with. I don't know.
So like up, down.
So many. Up, down.
Yeah, I mean, my idea was
Spin. The spin. They're like Ising spin, like spin 1/2.
Yeah.
It's just some electron. It's possible.
Something
Like an unpaired electron or something.
you have SI at RI and SJ at RJ, then basically it's like a cosine of mod RI minus RJ.
What's RI and RJ? Oh, the position? Yeah, exactly. Something like that. Yeah, it really doesn't matter. I mean, so you get some. So what I'm trying to say is just you get effectively some Hamiltonian of this form. Okay. Where these JIJs, okay, so since they depend on the distance, but the potential actually oscillates, can have like various signs. Okay, they can have like plus minus. It's sort of more or less random. Okay. So this is disorder, and this is because the distance between these atoms is can be anything. It's just sprinkled over it. There's no regularity in it. So it's disordered in a disordered system. And well, these, whatever they are, I mean, whatever your model is, it's just like spins. You can model it any way you want. Okay.
They can't decide whether it wants to be a ferromagnet or an antiferromagnet.
Yeah, that's right. Exactly. So these systems exhibit. So the key property of these systems is that they exhibit so-called frustration. And what does this mean? This means that you get. So when our 3 spins frustrated, here's 3 spins. So let's say you have 2 positive JIJs between these and then a negative coupling over here. Then there is just no assignment of spins. So let's say we indeed have just Ising spins like plus minus 1 or something, plus minus 1/2, plus minus 1. There's no assignment of spins that makes all of these links happy. Okay, so for example, if you put this one up, you would say, okay, well, then I have to put this one up as well to minimize the energy, and then this one should be down, but then this link is unhappy. Okay. You could try to flip this one. You could say, okay, I take this down. Now let's say then this one has to be down, maybe, and then this one has to be up. Okay, but this again. Anyway, whatever you try, it never works. Yeah. So whenever basically you have a closed loop where the product of all the signs is negative, you get this frustrated situation, and there will be a lot of such loops in these systems. Okay. The result of this is that that you get exponentially many local minima. Okay. Right. So, right. So what we will have actually in mind most of the time is the sort of the simplest model of a spin glass, sort of the hydrogen atom of spin glasses, and that's the Sherrington-Kirkpatrick model. Which for obvious reasons is usually referred to as the SK model. And so in the Sherrington-Kirkpatrick model, you take basically the interactions of infinite range. So you basically take all of the Jij's drawn randomly out of a probability distribution, which goes like e to the minus Jij squared over some, whatever, some spread a squared or something. Okay, so you just draw them out of a Gaussian distribution, all of the links, and you get random interactions between all lattice signs. Okay, so that will be sort of the model we have mostly in mind. But of course, it's not necessary. I mean, in real spin glasses, you have, of course, finite range interactions, but nevertheless, at least in some cases. Over here, well, here it doesn't. So, yeah. Well, so the I's and J's just label the spins. Okay. So they don't. But since the interactions are completely random, it doesn't matter how they are arranged. There's no longer a notion of distance or position.
Yeah, the IJ is not. You have a notion of nearest neighbor, right?
No, it's not nearest neighbor. That's the point. The Jij's. So the I. No, that's the point. That's the point. So this is they call it infinite range model, which means like you have interactions between any pair, completely random. Okay, so it's a simplification, but it's a useful simplification. Yeah. Okay. Very good. So you get a landscape, okay? That's the basic point. It's a very complex system, and essentially you get some landscape, okay, which pictorially, as you know, looks like this, right? That's a landscape. All right. I guess my time is more or less up, but let me just in words then. So okay, so these models exhibit some really remarkable phenomena, and sort of the underlying geometric structure under all of that is the so-called ultrametricity. So what does this mean? So one manifestation of this is that if you look at zero temperature at the ground state, okay, first of all you find infinitely many ground states, okay, not exponentially many, but infinitely many in the thermodynamic limit. And if you take any two of these ground states, and you pick just any two of the ground states, and you compute the distance between them. What do I mean by the distance? Well, you just take the difference of all the spins, you square that, you sum it up, and you take the square root of that, right? Just the natural distance. Then this exhibits so-called ultrametricity, meaning that if you draw a triangle showing the distances, so this is 1, this is ground state 1, ground state 2, ground state 3. This is the distance between 1 and 3, distance between 2, 3, distance between 1 and 2. You will always find an isosceles triangle, okay? You always find that 2 of the distance will be the same, the third one will be the shorter of the 3, okay? Now this may seem like really weird, and it is, but there is a situation where actually this ultrametric distance notion is very familiar, and that is in the context of just species, biological species. So we can define a distance measure between two species as how far back in time you have to go to find a common ancestor. And with that distance measure between species, you get this ultrametric structure, okay? So let's take, for example, a human, a monkey, and a snake. Okay, the distance between the human and the snake is the same as the distance between the monkey and the snake, and the distance between the human and the monkey is the shorter one of the 3, okay? So whenever you have such an ultrametric distance notion, you have the structure of a tree, okay? And so what this basically means, and what will show up, and which is sort of like at the core of the theory of the Sherrington-Kirkpatrick model, is that indeed you get a hierarchical organization of states into a tree-like structure, which of course has no evolutionary origin and so on, it's just purely static, but that is sort of at the core of the whole analysis. But more about that later.